Hola, señors.
Morning.
Hello.
Let's see, I was looking at our syllabus, which has there we go. Which I would say has changed here at the end. So I just wanted to update you on that. Last week, we really only got through velocity, which 16.5 was finding it kind of the hard way or the long way, and 16.6 was using the instantaneous center of rotation idea. That's really all we got to last week. So there's really those two sections. So what I want to do this week is talk about acceleration, and it adds it's good because it's kind of practice of what we did before, but it definitely adds a bit of pain in terms of like keeping all the pieces together. And we'll see how far we get. Maybe we'll get through it today and feel like we're pretty good. One possibility would be to spend I don't know. The thing I'd like to do though is have some time in class to review, because this test, it's just a midterm. It's just over this last material. Traditionally the grades aren't as good on this one because this is just kind of a hard concept. So the good thing is, I think if we, rather than pick up another section after this, if we kind of use the next 2 weeks to kind of make sure we understand acceleration and all the previous stuff and then take the test. So this last little bit's debatable. Let's kind of see what happens. But we'll talk about the test. Maybe that's the following Tuesday. Maybe it's the following Thursday, and we spend today and Thursday on acceleration and then Tuesday reviewing, and then you can sort of take the test after that. I'm kind of flexible. We'll talk about it.
What about the homework 16.6?
Ideally, it was my anniversary this weekend, so I was out of town. I didn't get any work done, but ideally you have 16.5 and 16.6 to me now already, if not soon. But 16.7 in a sense we haven't started till right now, so you shouldn't have any of that. I think I mentioned that going out the door Thursday last week, so you didn't stress out about 16.7, but I hadn't adjusted the syllabus and talked about it formally. So to answer your question.
Is that what it was? I just maybe I missed something, because I think you said that 16.5 is due and 16.6 we're gonna talk about it this week.
Maybe I did, and that's okay. Like, we're winding up toward a test, so if you haven't given me 16.6, but 16.6 is the instantaneous center of rotation technique for velocity, and we'll practice that again today as a part of kind of what we're doing here. So
yeah, I completely forgot what you said about not to 16.7, but I gave up on trying to get 16.7 done at like 2 a.m. last night. So it all worked out in the end.
Hard, yes.
Yeah, I gave it a stab and it was not. Yeah.
It's not human. So let's see if I can break it down for you in a way that you go, okay, I can do that. You're not going to say, oh, that's easy, just because it's kind of complicated. It's a lot to kind of keep straight, but fortunately it follows a similar pattern to what we've been doing. So let me introduce it to you. What are we doing? Somehow we're canceling here. Okay, so how does acceleration work? And I won't pull this up again, but you may be able to appreciate that these things are accelerating. Incidentally, do you see anything different now? Are you still seeing my screen like normal? You're still seeing it? Piece of paper, okay. Tell me if this isn't right. I switched computers to one that doesn't suck anymore. So, but you know, there's always little small issues. So maybe you agree that there's kind of acceleration built into this, like the Desmos I showed you where the control or I forgot what I called that, the driver was kind of cruising around the circle, and because of the connecting rod, it was sort of sliding back and forth in the piston. But we saw that it wasn't going the same speed all the time, even with a constant velocity on the driver and no acceleration at all. There was acceleration happening on the other side. It didn't just say the same speed over there, even though the driver was going at the same speed, cruise control, so to speak. And so really that's all we're going to tackle now is what if we get acceleration involved? But here's the kind of the new thing that we got to consider. And then we'll get after this. So intro to acceleration. And again, this is in the context of relative motion analysis. And I kind of like to throw, I don't know, terminology in occasionally. You know, I'm not a terminology person, but it's just kind of like, what did we just learn? Like, does this mean something to you now when you stop and think about relative motion analysis? Yeah, it's motion of one thing relative to another thing. So because they're connected by a connecting rod, then motion of one thing kind of affects motion of the other. And so relative motion analysis. But now we're going to include acceleration into that. And so we, in the past with velocity, we said, yeah, it turns out that if you have, let's see, I think I'm going to make this picture look kind of like the initial picture of this, of the problem that we're going to do. So if I draw, that's not a circle. If I draw a circle up here and I put a connecting rod on it someplace, say right there, we'll cruise that over to here. And then we'll give that as our driver, we'll give that kind of a speed. And so since there is a rod over here connected to the center, so really the red is dotted in the sense that that point is kind of cruising around. So awesome. I think I need to redraw a little bit though, otherwise this isn't going to look very good. Let's move it up here more. And we'll make the so what we said before with respect to velocity, so if this was, I'm going to use completely different letters here, but like this is M. We said if this is the velocity at M and this is driving it, and this is kind of the point P up here, we said that certainly the motion of M is going to affect the motion of P thanks to the green connecting rod. And we said that if you'd like to know what's going on with P, I'd like to know what the velocity at P is. That's the unknown, right? Velocity of M is maybe known if M is the driver. Then we say, well, first, it's the same as the velocity of M. In other words, you picture, I'm going to erase this, but just to remind you, you picture this as moving straight down. So it slid down. The green line slides down because the velocity of M is moving. And then secondly, this thing rotates back into position because really P is stuck staying on that circle, right? So the second part of this is, well, I guess the fact that P is rotating around point M. Isn't that right? Isn't that what we said before? And so we came back then and we looked at this picture. we kind of drew all of that stuff in. So we said, well, the real velocity of P is taking off at 90 degrees. That's the velocity of P, because linear velocity is always perpendicular to that axis around which it's rotating. I think I'm going to draw that again so that it looks like 90. So that's always perpendicular. So we know where velocity of P actually goes. But then given how that just rotated into position, I'm going to switch to blue. Then this velocity, which is also perpendicular to its radius, that is the velocity of P as it rotates around M. Isn't that what I said? You feel good about that? I mean, maybe good's a strong word, but you feel like you understand that? Well, let's go add acceleration to the same picture here. It's not going to work. So I'm just going to move this figure down a hair. So I have a little more room to work. So if I start adding acceleration to this, that's the question. Where does all of that go? So acceleration would look like this. I would just say, well, what if you'd like to know the acceleration at P? In other words, how is P accelerating? We know what its velocity is. And again, it's important to make sure, because I didn't put any numbers to this. This is the driver and P is the follower. So no different. Acceleration of P is the same as, well, whatever the acceleration of M is. Whatever the acceleration of M is, it's going to match. Starts out with the acceleration of M, but then it would be plus the acceleration of P as it rotates around M. And so I can draw all of those things in. So down here, there'd be an acceleration of M as well. Maybe V, maybe that's not just a constant velocity. So later today, we'll say, okay, that thing is 5 feet per second, but then it's increasing at 2 feet per second, that kind of a thing. So maybe it actually has an acceleration. So where does that go? That's kind of the key.
Well, we could break up further and break the acceleration of what? How do you call it? P over M into
Yeah.
its normal and tangential components.
Yeah, that's exactly right. And the key is you don't actually have a choice. You have to do that. So acceleration of M ultimately has, let's see, I think I'll do this in red. Acceleration of M really has a tangential and normal component. Let's see, where would the acceleration of angle, that angle be? In reality, this is the acceleration of P. But remember, specifically, that's a tangential component. Remember, acceleration has a speed change component, and that was the tangential one. But then it also has a direction change component. And so if I come back over here, that is the acceleration of P, but that's its normal component. So there's actually two components to that acceleration of P that we're interested in, which means M was linear if it's stuck in there, but ultimately acceleration of P has got a couple different components to it. So and can you predict where this is going to go with respect to the other one as well? If I switch colors to, I guess let's go with green. I haven't seen a lot of green. Then wouldn't this up here, because it's again, perpendicular to the radius. Isn't this up here the acceleration of P with respect to M? Which one is that, tangential or normal? Again, you got to pay only attention to the green line and the blue arrow that we're up at. But that's tangential because it's a speed change. Notice they're both the same as, well, their velocities were. Velocity is here. Velocity is here. Well, that's where tangential acceleration goes. Velocity is here. That's where tangential acceleration goes. So this is P of M tangential. And the normal change of speed is pointing toward the center around which it rotates. And that's P as it rotates around M. And so that is going to be in this direction. And so this is splittable into the same thing. It's tangential and normal components. So that just means if I want to get acceleration involved, wow, that's going to be a pain, because acceleration has two components to it. You're just stuck with it. You can't just leave the blue equation alone that we originally made here. You don't have a choice. And so this just creates, man, just unknowns kind of everywhere. Okay. That hurts. But then second of all, because, maybe we'll need to know this, but you may remember that a couple of formulas that we had that pertain to this that seem like they should be black, but didn't we have some formulas for like what was tangential acceleration and what was normal acceleration? What were those? Looking at your note sheet. These formulas. So I'm going to consider that one because it pertains to velocity, but this is the velocity divided by the radius squared. And tangential acceleration was the angular acceleration times the radius. So I'm going to need to get those involved too, so that I can speak about them. So just as a precursor, do you remember in the last section, and you can see why this is going to get complicated and painful for us. Do you see that in the last section we were able to figure out these angular speeds? We found angular speeds, not angular accelerations. But perhaps I can get this involved. And then certainly this one's even better. This one's a lot better because I was able to find the velocities. And this is saying if you'd like to know these normal accelerations up here, these two normal accelerations, like I'm gonna actually be able to replace that with velocities. So that's kind of cool. Like that might save me some trouble. So let's think about that and just slowly and carefully wade into our first example that is similar. Find the angular acceleration of link CB. Angular acceleration of link CB. So that is CD or BC. And as I like to say, just to make this a little bit clearer, rather than just saying BC, is saying, well, B is actually rotating around C. So I kind of like to designate this as B as it rotates around C. I just think that's nicer, even though which way that rotates, maybe you remember, doesn't make a whole lot of sense. And then secondly, the acceleration of B and the acceleration of B. So just the regular, notice that doesn't say tangential or normal, it's just what's the acceleration of B. So this problem isn't asking about velocity, but unfortunately, we're actually going to need velocities. The velocities we did in the last section, we're going to need them to answer this question. That's the thing that's kind of a challenge about it. So let's get everything kind of written in here. So let's see, the snapshot in time is when theta equals 34. Notice I made this as easy as I could because I didn't have to give you an angle to tell you where B is since it's straight up and down. So there's only one angle in this picture. So maybe that'll make our life a little bit easier. So cool. And I got a couple links. I know that AB is 1.5, BC is 5.8. I don't know how busy this drawing is going to get, so I'll leave this alone. But let's kind of at least work the color thing a little bit here. And we'll say that, okay, cool. I know the velocity of B. And again, can you distinguish that C is being pulled straight down, that's going to cause this graph to rotate? I guess that would be counterclockwise. So that'd be the velocity of B right over there. It's going to get pulled in that direction. And while we're at it, let's go in and add all those accelerations. Like, isn't that also the tangential acceleration of B? So it's not just tangential acceleration, because I'm going to have to do this in other places, but it's the tangential acceleration of B. And then hopefully that's visible enough. That would be the normal acceleration of B. And again, we know that that's 90 degrees. And so there's those terms. Okay, cool. And then in blue, let's go back and again, I wonder if you can see which way this is going to work. So I already drew this for you a second ago. It's going to pull straight down, and then it's actually going to rotate around C. I guess that would be in the counterclockwise direction. So again, I'm going to try to draw 90 degrees to that, at least reasonably accurately here. So that would be the velocity of B as it rotates around C for the second part of its translation, and then a rotation. So the second part of that transformation is a rotation to get back into position. And then just like before, that is also the location for acceleration of B as it rotates around C, but tangential. And then if we pull down in here, that would be the acceleration of B as it rotates around C, normal. So I've got everything kind of filled out. So the question is, I know exactly what's happening at C. It's going straight down at the snapshot in time, 5 meters a second, but it's speeding up at 2 meters per second. But the question is, what's happening up at B? So of course, our basic question is, what is happening up at B? I'd really like to know what the acceleration up at B is. And we said, well, what happens up at B is this is caused by what happens at C, but then, and that's the translation plus the rotation. So that's acceleration of B as it moves around C. And we ultimately agreed, remember, that the actual accelerator, I think I'll erase this, but I think I'm definitely going to erase this, but let's just look over here at the red stuff. If I redraw the acceleration of B normal in this position, then this is actually, this right here, that's actually just the acceleration of B. Remember that? In other words, it's going in a weird direction. It's a combination of those two things. And I told you before, that always bothered me because acceleration of B tangential is literally a speed change, whereas acceleration of B normal is a direction change. So the fact that I'm adding a speed and a direction change together, it allows me to write it as one number, but it feels like it should be left broken out. So just an interesting side note. So what we're saying is we're actually going to replace this. Maybe I'll just replace it. Yeah, I'm not going to replace it. I'm going to leave it written there, but then cross it out. We're going to replace that with acceleration of B with respect to C tangential plus acceleration of B with respect to C normal. So that's kind of our new equation then. So as before, let's see if we can get this going in the right direction. So as before, we said we have a horizontal equation, in other words, X to consider. So, what would that look like? Well, all I'm going to do is just rewrite that with a bunch of X's in it, but just to get it kind of rolling. So I'm saying acceleration of B, except only in the X direction, equals acceleration of C, but only in the X direction, plus acceleration of B with respect to C tangential, but only in the X direction. So now based on the drawing, do we know any of those? Like, is there something I can replace those with? Do I know anything? Well,
we
fire away.
yeah, just looking at ACX, it's just moving along the y-axis, so you can ignore that.
Correct. So in other words, this one is actually 0 since C is in a cylinder that's forcing it vertically, then it isn't going to be accelerating left and right. So that's something I could know. What about acceleration of B in the X direction? If you look up there at B, what's its accelerations? Again, you're looking at these two. There's its accelerations. We're talking about B, not B with respect to C, that's up here, but just B. So I'm looking at that acceleration and that acceleration. What does that inform me? Well, because B was in such a nice position, notice acceleration of Bx is actually the same as the acceleration of B tangential. They're the same. I didn't have to multiply it by the cosine of 20 degrees or something like that. Although if it wasn't where it is, I would have had to do that. So the thing is perfectly, well, leftward. And maybe, and again, we talked about the fact that signs are a little confusing, but I find myself thinking, let's see, if velocity is left, again, we just decide, am I just going to say, well, I see that it's left, and so let's not call it negative. Or you might say, well, no, actually, I do want to call it negative because it's facing left. I'm going to consider the sign convention. So I think I'm going to choose that to start with and call that negative. Now, and again, the goal here is to try to minimize the number of unknowns. Do you see that I've got an equation there that actually has 4 distinct unknowns in black? And so 0 was nice because it actually got rid of one of them. The acceleration of B tangential over here really didn't do much. It just changed that to the same. I mean, it's still a variable. It's just different looking, but I never wanted to know about X. I wanted to know about acceleration of these points themselves. And so this is a better way to write it, but that didn't help. It's still just a letter I don't understand.